Given that the Young's modulus of steel is 2 times 10 to the 11 Pascal, how much would a steel cable stretch under 2,500 newtons of force if the cable is 25 meters long and has a diameter of half a centimeter? So this is a question that I think I'd like to start by just stating what the Young's modulus is. That's my starting point for something like this, because that's something I can remember. And then I'm going to look at some of the information that's given to me here, because I think if I can figure out, like, what do I know and what am I asked for, I can probably figure out what I need to do with this. Now, one of the things that we're given there is we're given that Young's modulus of 2 times 10 to the 11. And what is that new thing? I called it a Pascal. That, it turns out, is the SI unit of pressure. It's a derived unit, and it's actually equivalent to a Newton per meter squared. So maybe to make things a little more straightforward for us, I'll call it that. And that might make sense, because if you look at the definition of the Young's modulus, it is force per area as a ratio and then divided by another ratio that really just length per length. So that doesn't contribute any overall dimensions to this thing. So really the dimensions of force per area is what this should have. So that's kind of how that unit might make sense. Now we're given here a force of 2,500 newtons. We're given, I think it's safe to say that L naught is equal to the 25 meters of the cable length that I'm given. And okay, well, what else might we like to have? I'm given a diameter. This formula has area in it, right? Well, okay, so I've got like a diameter D is equal to 0.5 centimeters. Maybe one way I could think about that is to say, okay, but that means I have a radius that's equal to 0.25 centimeters, which is really going to be equal to, in meters, 0.0025, again in meters, running a little bit out of space there. That would let me calculate that area. So recognizing that area is what's in this formula, I'm going to go ahead and do that. So we're thinking about pi r squared, standard area of a circle. Because a cable, I usually look at the cross-sectional area is probably given by a circle, and we were given diameter there, so that makes sense, I think, to do this. So in my calculator, I'm going to use my pi button and multiply by 0.0025 squared, and that should give me an area in meters squared. And let me go consult my calculator. I think this is going to be a kind of small-ish number of 1.96. Now let's see, we're probably working, I don't know, I guess 2 sig figs or something there. Let me keep at least 2 more then, so, or well, 2 beyond that, so 1 more than what I have. So it's 1.9634, etc. But I think maybe just 1 more, 3 is good enough. And then it's actually times 10 to the minus 5 meters squared. So that's the number that I got for that. Now we're asked for the amount of stretch. So the thing to recognize here is this really is the question. Okay, so maybe now I can go over here and do some algebra with that. Or you might recall from the key concepts page and video, it was really on the whiteboard part actually when we did that, is I think I solved for, let me make sure I get this correct. I think it looked like this for the amount of stretch as a function of all the other things. And if we were doing this live in a classroom, I'd ask everyone to check my algebra, but I think we'll skip that right now. Anyways, at this point, though, I could go ahead and start to put in the numbers that I have. And I'm going to still maybe like to put in units just to make sure everything is okay. This area one's kind of annoying to put in, I guess, but oops. I forgot a number there. 963 times 10 to the minus 5. Okay, so I regret not making that fraction large enough. If you experience things like this at home, well, you're just like me, maybe. Anyway, so, and then we have the 2 times 10 to the 11 newtons per meter squared. And oh my goodness, you know, I have the F kind of floating off to the side here, but maybe it'd be cool if I just put that up here, the 2,500 newtons, because that is algebraically equivalent. And we expect, right, it looks like units-wise newtons disappear, and I think, let's see, actually it looks like these two cancel as well, and it makes sense. We're supposed to get something in meters, right? So I went and put this in my calculator. I actually had an unrounded version of this number that I put in here in case that makes a difference if you're trying these calculations at home yourself. But I think at 2 sig figs that probably won't make a difference. And because I got like 0.0159154,943. If you round it off somewhere, you might be a little bit different somewhere out there. But I think if you round that off to 0.016 in meters, that should hopefully agree with what I have there. Let's go ahead and check this answer. Oh, did we get it wrong? It says 1.6 centimeters. Well, wait a minute though, but 0.016 meters is equal, right? This is equal to 1.6 centimeters. So this is actually okay. And this can happen sometimes because I know like in this class, you have a lot of, I think there are homework questions and you'll be able to look up answers for those. And you might report an answer different than mine because of a unit thing. You might also have rounded off a little different than I did somewhere too. So sometimes those things are there and you have to recognize either I'm close enough or, hey, it could be in different units. That's okay. There's no rule really out there saying that I have to answer every question in base units. They're convenient for the calculations, for tracking units. It's easier. But there's nothing saying I can't use centimeters to report an answer.